Alright, so this video is going to be on calculating differentials. Now, each of the differentiation rules that we had can be written in differential form, okay? The constant multiple, the derivative of cu equals c times the derivative of u, right? In this case, when we're talking about differentials, we're just going to say d, right? So du is the derivative of the function. It's the differential u. So we know we can take the derivative. We can pull the constant out. If we take the differential of a sum, it's just the individual sum or difference of the differentials. Product, same deal. Quotient, same low d high minus high d low over low low. So my question is, what's the difference? Well, here we go. If we're talking about a function, we know that the derivative is y prime equals 2x, right? The differential dy is 2x dx. Okay? If we've got the square root of x, then I know that y prime is 1/2 x to the 1/2. Right? Or 1/2 square root of x. Is everybody comfortable with that? Let's take this back a hair just to say that this is equal to x to the 1/2, right? So y prime, we bring the 1/2 out front, x to the negative 1/2. Maybe easier if you see it like that. So this is just going to be 1/2 square root of x. The differential dy would be 1/2 square root of x dx. Alright, y equals 2 sine x, then y prime equals 2 cosine x, right? Because the constant just comes out, take the derivative of sine, which is cosine. But then that means that dy is 2 cosine x dx. Do y'all see the pattern here? We're just taking the derivative and tacking a dx onto it, basically. So we've got y equals x cosine x. We're going to do y prime equals first times the derivative of the second, plus second times the derivative of the first, right? Then what's dy going to be? Negative x sine x plus cosine x, all quantity dx. Okay, it's kind of important that all of that is being multiplied by dx, okay? 1/x, we know y prime is just negative 1/x squared, and we know that dy is going to be negative 1/x squared dx. Alright, so the notation that we just used in that example is called Leibniz notation for derivatives and differentials, and it was named after Gottfried Wilhelm Leibniz. You may be familiar with him a little bit from Sheldon Cooper, or you may just be familiar with him because you had a math teacher that explained the difference between Newtonian calculus and Leibniz calculus, which is very little only notation generally. So differentials can be used to approximate function values. Now to do this, we're going to go back and use this f of x plus delta x, right? So I know that f of x plus delta x can be approximated by f of x plus dy, right? Because remember, dy equals f of x. Yeah, I'm not going to write it out for you. This is all just derived from the stuff from the earlier part of this section. But we know that dy can be approximated as f prime x, right? So the key to this formula is choosing a value for x that makes the calculations easier. So this probably doesn't make any sense right now, but I'm about to show you a problem, and you're going to see exactly how this is going to work, okay? So I'm going to use differentials to approximate the value of the square root of 16.5. So here I'm saying f of x equals the square root of x. That's my function, right? Inside of this, I'm going to write that as 16 plus 0.5. Why? Because the square root of 16 is something that I can easily take the square root of, right? So I'm going to say that we're actually saying okay, we got f of x equals square root of x, but what we have is f of x plus, what's the notation we're going to use? Delta x. And that's going to give us, in this case, x equals 16 and delta x equals 0.5. So I've got a formula, right? I know that if I just add f of x plus f prime dx, I can just plug all this in. So this means that f of 16.5 equals f of 16 plus f prime of 16 dx, but dx is 0.5. So if I know that the square root function is my f of x, I know that f prime of x is 1 over 2 square root of x. So I can just plug these values in. So I'm saying f of 16, that's just going to be square root of 16, plus f prime of 16, which is 1 over 2 square root of 16, times 0.5. So that gives us 4 plus 1/8 times 1/2 effectively. So 4 plus 1/16. So this is going to give us, what, 65/16. So if you put that in your calculator and ask for the square root of 16.5, you can find the square root button. You get 4.0620192. Oops. We know the actual value is 4.0620192. And then I do 65 divided by 16. I get 4.062. 4.0625. It's a pretty good approximation, right? There's no possible way that I could get a better approximation just by guessing, right? I know it's going to be a little bit bigger than 4 because, you know, square root of 16 is 4. This is a little bit bigger than 16, therefore your square root is going to be a little bit bigger than 4. There's no way I could have guessed it with that kind of accuracy. So basically what you're looking at is trying to change the inner function into an x plus delta x, and then evaluate the function, evaluate the derivative, and then tack it all together there at the end. So if you have any questions about approximating a function value, just shoot me a reminder or ask a question in class.